Hello, and welcome. So what we're going to do today is we're going to review 6.4, which talked about vectors and dot products, and 6.5. And I want to go ahead and start off I was going to end with this, but actually I think this might be a nice way to start the video. So I want to start with something that I would consider to be mathematically beautiful. So how does this sort of newer stuff help us see some beauty in math? And this is my favorite proof of the Pythagorean theorem of all time. In fact, it's a Hungarian proof. I saw this when I was studying in Hungary. And it's really simple. It's just based on what I just taught you guys about trigonometric form. And it just works out. It's just awesome. So let me go ahead and sketch out the idea for the proof. So we have, consider we have the imaginary coordinate system, right? So this is we call this the real axis. This one up here is the imaginary axis. And again, we use this coordinate system when we want to basically visually show what a complex number looks like. So let's suppose I have a complex number right here. We'll call it z. And you can visualize it either as a point or, kind of like a vector. We went over the fact about how complex numbers are very, very similar to vectors. So you can sort of interchange them, except you can multiply complex numbers, right? You can't multiply vectors. So that's my complex number z. Let's say it has coordinates a plus bi, right? So remember, as far as complex numbers go, the a is your real component, right? So we would say this is a, and the b is your imaginary. This is b. And because we sort of have a triangle here, let's go ahead and just sort of label this side over here as c. Now, based on what I taught you guys in 6.5, there's another way that we can express this complex number, right? If we know the angle, this is sometimes called the modulus, but basically the angle that the complex number makes with the x-axis, we can also express it in what's called either trigonometric form or polar form, right? So this one over here that we already found is rectangular form. And polar form is the magnitude of the complex number or absolute value. So that's c. Sometimes it's called r, right? That's okay. Times cosine of the angle plus I sine of the angle. Right, so this is called polar or trigonometric form. And sometimes the c is an r. That's okay. It doesn't really matter what you call it. I'm calling it c for the purposes of this proof, though. Think back. I don't know if you guys remember this. Think back to what a conjugate was. What is the conjugate of a complex number? Well, the conjugate would be a complex number that would be, in this case, the conjugate of z, right? We usually write a little bar above it, is going to be a minus bi, right? All you do is you change this little plus into this minus here, and that's called the conjugate. Conjugate. And if we were to graph this point, it would be symmetrical, right? It's down here, and we have sort of an arrow going to it like this, right? And we have a line going like this, right? So we still have that length of A, right? This is a length of B, so this is still a length of C, right? We're talking about lengths here, so the B doesn't have to be negative in this case. And down here, what is the angle? Well, this is a clockwise measured angle, so this angle right here is negative theta. it's an angle with the same size, but it's going the opposite direction. So what would be the polar form or the trigonometric form for this complex number? Well, it's still going to be c, and then it's going to be times cosine of negative theta plus I times sine of negative theta, right? Because we're going clockwise to get to the conjugate. Now, if you remember the even and odd properties for sine and cosine, you can simplify this. So you end up with c times cosine of theta, right? This negative goes away. And then the negative inside of sine just goes out to the front. Right? So we have minus I sine of theta. All right. Cool stuff, cool stuff. So this is the polar / trigonometric form here. And of course, we have the rectangular form here. So why am I showing you all this? Because we need these things in order to prove the Pythagorean theorem is true. All right, this is so nice. All right, you have two separate ways of computing the number z times its conjugate. Right, so z times its conjugate. There are two ways you can do this. One way is completely in a rectangular fashion, right, using the rectangular form. Right? So if we do z times the conjugate, that's the same as a plus bi times a minus bi. And if we multiply all this out, what do we get? We get a squared minus abi plus abi, and then minus b squared I squared. Now those two middle terms cancel out, and if you notice, right, this minus b squared I squared, remember I squared is -1, and we have another negative there, so that's going to turn into plus b squared. Right, so think about that if that doesn't make sense to you, right? The a squared goes here, so if you do this in rectangular form, you have a squared plus b squared, right? This is the one version of how to calculate z times its conjugate. The other way is using the polar form, right? So we could also multiply the polar forms of each of these numbers. So let's see how that goes here. The polar form of z is going to be c times cosine of theta plus I sine of theta. That's the polar form for z. And then we have times the polar form for the conjugate, which is c times cosine of theta minus I sine of theta. Right? So this is z, and this is z bar, the conjugate. All right, so let's go ahead and multiply these out. What I'm going to do is I'm going to collect the c terms in front. C times c is c squared. And then I have cosine of theta plus I sine of theta times cosine of theta minus I sine of theta. And this is where it gets really, really good. So let's go ahead and distribute out these parentheses here. We end up with c squared times, this is cosine squared theta. Now we have minus I cosine of theta sine of theta. That's the first, this thing. Then if we do this bottom one, we have plus I sine of theta. I'll write the cosine first. Sorry. I cosine of theta sine of theta. And for this last little distribution, we have minus I squared sine squared theta. Right? You should have 4 terms because we just distributed. Now, if you notice, right, the middle terms cancel. Right? So we're left with c squared times cosine squared of theta. And then what does this minus I squared sine squared turn into? Well, it's going to turn into plus sine squared theta, right? Negative I squared turns into positive 1 because I squared is negative 1, and we have another negative there. And what does cosine squared plus sine squared turn into? That turns into 1. So what we have here is the left side. The left side turns into a squared plus b squared. And we have that the left side should be equal to the right side, which is just c squared. And that right there is the Pythagorean theorem, which is beautiful. Right, so these two forms for complex numbers, because we have two ways of doing the same calculation, we know that the end results should be equal to each other, and it proves the Pythagorean theorem. So that's a nice little Hungarian proof for you. So anyway, I want to spend the rest of this video sort of going over some more practice with mostly with complex numbers, because it's been a while since we've touched those, and I might throw in some vector dot product stuff at the end. So we'll start with these four. It says find the absolute value. And depending on which form you're dealing with, you're going to have to go about doing these different ways. So I'll go ahead, I'm going to start with like 2, I'll do 2 and 4 first, the rectangular forms. Now for rectangular form, what you want to do is you want to recognize your A and your B. And we learned, I think it was in 6.5, that if you're taking the magnitude of, I'll put the I first, I guess, IB. Sometimes you see it as BI or IB. It doesn't really matter which order, right? But if you're taking the magnitude of a complex number, the formula for that is going to be a squared plus b squared inside of a square root, right? It's basically just the Pythagorean theorem. You're squaring each component, adding them together, and then you take a square root. Right? That's the formula for magnitude or absolute value. Right? They're kind of the same sort of thing. So in this case, we would do negative 5 squared plus 6 squared inside of a square root. So we have 25 plus 36 in a square root. And remember, right, y'all are going to have a quiz the next class after the weekend. So stuff like this could easily be on there. So 25 plus 36 is 61. And you can just go ahead and leave it in the square root. That's fine. There's no real reason to get the decimal there. And with 4, it's going to be the same thing. You might be wondering, what's the component, the imaginary part, right? Well, it's just going to be 1, right? Because if you have I by itself, the coefficient is 1 there. So you would do the same thing, right? The magnitude of that is going to be negative 6 squared plus 1 squared in a square root. So we end up with 36 plus 1 in a square root. So that's square root of 37. Nice. Now let's get over here. So let's do 3 maybe. I'll get back to 1 in a second. We still do this the same way. You just got to be a little bit more careful, right? So this is your A. This is your B. And so we just want to run the formula the way we always do. So we're taking negative square root of 66 over 2. We're squaring it. We're going to add to that the square root of 66 over 2 squared, all inside of a square root. I'm still using the same formula. It's no different. Right? Now when I square those two, I get 66 on top and 4 on the bottom. And then plus another 66 on top, 4 on the bottom, inside of a square root. Okay, let's see, this turns into 132. Let's see, 120 plus 12. Yeah, 132 over 4 in a square root. We want to keep going here. Simplifying that, we get 33. I think we get 33 inside there. Yeah. Square root of 33. And that is our final answer. That is the absolute value of that complex number. Remember, absolute value just means the distance from the origin. So that's why it looks so similar to the Pythagorean theorem, because you can basically create a right triangle, and that distance is the hypotenuse of the right triangle. But how do we do this with polar form or trigonometric form? It's actually even easier than what we were doing before. We actually don't even really need to use a formula. So you guys can just remember this. If you have a complex number in polar form, polar or trig form, right? Those mean the same thing. If you have it in that form, this is your absolute value. That is your magnitude. That is the distance from the origin to the number. Because think about it, right? This right here is essentially has a magnitude of 1. It's basically a complex number that's on the unit circle. So it's a distance of 1 from the origin, and that we are scaling it. We're scaling that number by the square root of 10. So you can think, basically the right part puts the complex number on the unit circle, and then the left part, that scalar, sort of stretches it out so that it goes further away. Or sometimes it gets closer, right? But basically that number in front is your absolute value. So you would just say the square root of 10 is my absolute value. Now, if you try to use the formula, it's still going to work, but you're going to end up with the same answer. You're going to end up right back to square root of 10 because that is the right answer. So the formula still works, but it's just kind of obnoxious to use here. And what's going to happen is you'll end up with cosine squared plus sine squared, and those two things will turn into a 1, and all you'll be left with is the square root of 10 anyway. So it works itself out to the same answer if you want to use the formula. So just keep that in mind. Polar form is nice in that regard when you're doing absolute value. Okay. In these problems, we're trying to simplify a complex number that's raised to a certain power. Now, just like in the last one, there's one of these examples is going to be easier than the others. But for some of the others, we're going to need to know a certain theorem. So if you remember, I might spell this wrong, but there was something called de Moivre's theorem, which basically tells you what a complex number raised to a power turns into, right? So let me write out sort of the formula for it. So if you have, and the formula used R instead of C. I used C in that proof down below, but R works too. So if we have, let's say, this complex number raised to a power n, we don't know what n is. It's just some natural number, right? Like 2 or 3 or 4. That is going to calculate out to the same answer as taking r and raising that to the n times the cosine of n times theta plus I times sine of n times theta. So that's a really nice little formula here. So all we have to do is we have to multiply the angles by n, and then we have to raise essentially the absolute value to the power n, right? Remember, the r represents your absolute value or magnitude. You just raise that front number to the power of n. So for polar form, it's not too bad. So here's a little quick concrete example, right? So essentially, right, we're taking 3 pi over 4, and then we're multiplying it times 3. Same thing over here. We're going to multiply this by 3. And then we're going to take the square root of 10 and raise that to the third power. Right? So we're not multiplying by 3, we're raising to the third power. So let's go ahead and do that. What do we get? All right, so square root of 10 to the third power. On the inside, we get cosine of, looks like 9 pi over 4 plus I sine of 9 pi over 4, right? So we just multiplied the angles by 3, raised the square root of 10 to the power of 3. And that's all we did. And now we can simplify this. We want to write our answer in rectangular form. That's what they say. I see. Write your answers in rectangular form when rectangular form is given, and in polar form when polar form is given. Okay. So actually maybe in this case we actually just keep it like this. Yeah, because this is already polar form. So we want to keep our final answer in polar form as well. So let's see. Depending on how you want to simplify that front number, you could write it this way. You could say that this is 10 to the 3 over 2. That's one way you could write it. You could write it as 10 square root of 10. That's another way. I might just stick with 10 to the 3 over 2. And of course, we just keep these like this. Right? We want to keep it in polar form. And there we go. That is our final answer, right? We wanted to keep it in polar form. All right, let's go up here. Yeah. Let's go up here. So same rule here, right? So we're going to multiply the angles by 2, and we're going to raise the magnitude to the power of 2. So this is going to turn into 2 to the power 2 times cosine of 315 times 2 should be 630 degrees plus I sine of 630 degrees. And what we want to make sure we do too is we want to make sure our angles inside of cosine and sine for the polar form, we want to make sure that they're less than 360 or less than 2 pi, depending on if you're in radian or degree mode. So in the front here, we're going to have 4. And what we want to do is if our angle goes above 360, just subtract 360 from it. So if we subtract 360 from there, we get, let's see, 270, I believe. 270, let's see. 270 plus 360 gives you 630, yeah. So sine of 270. So we can subtract 360 because it doesn't change the output of cosine or sine, right? Because remember, those are the x and the y coordinate on the unit circle. If you go around 360, you end up right back where you started. So we are allowed to do this, and it doesn't change the value here. So this is our new complex number in polar form, right? Because we were given polar form as well. So that's what we wanted. Let's go over here. Let's do this one, right? So here we have polar form again. Again, we multiply the angles by 3, and we raise 4 to the third power. So we have cosine of, this will be cosine of 2 pi. Well, that's nice. Plus I sine of 2 pi. And 4 to the third power, this is my favorite number, 64. And we just want to leave these alone. Nice. Now, if you really wanted to, right, you could very easily figure out the rectangular form. Right? So, technically the instructions are asking you to box this, right? But you could pretty easily figure out, oh yeah, cosine of 2 pi turns into 1, and then sine of 2 pi is 0. So really, this is equal to 64. right? It's actually equal to the number 64 in rectangular form. You could do the same thing with these other ones too, right? Like you could actually figure out, cosine of 270 is equal to 0. Sine of 270 is equal to -1. So like this complex number is equal to negative 4i, right? That's the rectangular form. And, you could do the same for this one as well, right? Cosine of 9 pi over 4 is going to be, I should have subtracted 2 pi from these angles before. Yeah, we weren't quite done with this one, were we? Yeah, I should have done that. 9 pi over 4 is bigger than 2 pi. Right? 9 pi over 4 is the same thing as just pi over 4. So we should have changed those. It's my bad. Yeah, so this would be our final answer. That's a more proper way to write it. But to get rectangular form, you would just calculate this, square root of 2 over 2. You would calculate the sine, square root of 2 over 2. And then you would just multiply it out, right? So you get, oh gosh, that would be kind of a mess here, but, there would be this times square root of 2 over 2 plus I times square root of 2 over 2. And, you would just distribute this in, figure out what those multiplications would be, and that would be your rectangular form for the complex number. I'm just trying to show you guys that you can always go from polar to rectangular or rectangular to polar. But anyway, let me go back here. Now we have a rectangular form complex number raised to a power. So what do we do about that? Well, if the power is small enough, we literally just multiply it out, right? So we literally just rewrite it. So instead of having to the power 2, we just have 2 of them multiplied out. And then we literally just multiply it all out. That's all we do. So we get 25 minus 15i minus another 15i, and then plus 9i squared. All right, so this is 25 minus 30i. And what does this turn into? It turns into minus 9, right? Because I squared is equal to -1. That's the most important part about I, is that when you square it, it equals a negative number. So 25 minus 9 are the only two that we can put together here. Right? Those are real components. So we end up with a final answer of 16 minus 30i. And that is rectangular form, and that's our final answer. So you might notice, right, the polar ones are a little bit easier to deal with. You don't have to distribute anything. You just have to make sure that the angles inside are less than or equal to 2 pi. So like this one over here, you could have changed these 2 pi's to zeros if you really wanted to. But at that point, it's just kind of preference. So as long as your angle is less than or equal to 2 pi, that's fine. Cool. Let's go ahead and work with some of these. So here, they want us to change from one form to another. So polar to rectangular or rectangular to polar. And I'm going to hold off from 10. I want to jump to one of the others. I'd rather do, maybe we start with 12, right? So 12, how do we get this to be rectangular form? Well, you literally just evaluate the sines and the cosines and then sort of multiply everything out. Right? Cosine of 0, we know that's equal to 1. Sine of 0, we know is equal to 0. Right? So this turns into 2 square root of 3 times 1 plus I times 0. Well, I times 0 is just 0. Right? So really, we just have 2 square root of 3 times 1 plus 0, which is just 2 square root of 3. And that's my final answer. So this is, I know it's just a real number, right? It doesn't have an I in it. I guess what you could do, if you really want it to be fully in rectangular form, you could say plus 0i. That's fine. You could do that. But really, basically, the rectangular form for this complex number just has a real component. The imaginary component is 0, so the I goes away. But that would be your answer. So this one turned out to be kind of simple. What about something like this, though? So again, do the same thing. So let's figure out what the cosine and the sine are. Cosine of pi over 6, we know that's radical 3 over 2. Sine of pi over 6 is going to be positive 1/2. All right, so let's rewrite this here. We have radical 3 over 2 plus I times 1/2. And let's go ahead and distribute this in, right? So with square roots, you can multiply the 3 and the 26 and keep that inside of the square root. So we can have, let's see, 3 times 26 is 78. Yeah. So we have the square root of 78 over 2 plus I times the square root of 26 over 2. And I'm just trying to see if, does the square root of 78, does that simplify at all? Okay, so that's 2 times 39. 39 is 3 times 13. No. Yeah, this is as simplified as we can make it, right? So this is the rectangular form for that polar complex number. All right, let's maybe do another polar one. So polar to rectangular. Again, what is cosine of 2 pi over 3? That's going to be, I believe, negative 1/2 from the unit circle. Sine of 2 pi over 3 is radical 3 over 2. So let's see what we got. 4 square root of 2 times negative 1/2 plus I times square root of 3 over 2. All right, now let's go ahead and multiply these in. So we end up with negative 4 square root of 2 over 2 plus I, and we have 4 square root of 2 times square root of 3 is going to be square root of 6. And then we have that 2 on the bottom there. So you don't want to stop here, though, because we can simplify this part and this part, right? 4 over 2 is just 2. So we end up with negative 2 square root of 2 plus I times 2 square root of 6. That right there is the answer. Again, keep in mind, right, I could also write it with the I coming after the component. That's fine too. Doesn't really matter if the I is in front or at the end. And then this guy. So this guy, I guess, is in rectangular form, right? Because, right, think about it. We could write it like this, right? That's rectangular. And sort of the question is, how do I get this into polar form? So this is where you need to get a little bit more analytical. So the first aspect to polar form, so keep in mind that it looks like this, is essentially, well, the magnitude or absolute value always goes out front. So if you're going from rectangular to polar, what you need to do is you need to say, what is the absolute value of this number? And you want to sort of pull it out of both components, right? So the The absolute value here, the absolute value of 3i, if you just do a quick calculation, it's just going to be 3, right? Just use the formula. Or better yet, right? Let's just go ahead and go through it. The absolute value of 0 plus 3i is equal to 0 squared plus 3 squared inside of a square root. That's the square root of 9, which is equal to 3. So the first thing we want to do is we want to pull out 3. So we want to rewrite it like this. Right. So we pulled out the 3, and then we want to ask ourselves, where is this on the unit circle? Where is that on the unit circle? 0, 1 is at the angle of 90 degrees. So we could either stick with degrees or radians. It's up to you, but we could easily rewrite this as 3 times cosine of 90 degrees plus I sine of 90 degrees. And you can pretty easily double check this too. If you don't know if that's the right angle, well, what is cosine of 90? That's equal to 0. What is sine of 90? That's equal to 1. And that does in fact turn into what we have there. So that's an easy way you can double check your angle. It's just evaluate sine and cosine there. And this right here, look at what we have. This is the polar form. That's polar form, right? We have the absolute value in front, and then we have our angle that the complex number makes. And if you really wanted to double check, right, you could very easily figure out where this complex number is. The complex number is 0 plus 3i. If this is the imaginary axis and this is the real axis, this is where 3i is. And this is, our arrow would be pointing straight up like this. And what is this angle? That's 90 degrees. What is the absolute value or the magnitude? That's exactly 3. And so, if you did this graphically, you could literally just take the 3, put it in front, and then take the 90 and put it inside of your sine and cosine. So if you're more of a visual graphing-based person, you could try to graph it first and then just plug it into the polar form. That's perfectly fine. So you have two approaches, right? You have two approaches here. I'll actually leave this part up. All right, and then, so we already went over this nice little proof. I think I've gone pretty long, so I'll hold off on the vector dot product stuff, but I do want to show you all this amazingly beautiful formula. This is probably the most beautiful thing I'm ever going to show you this whole year. I know I've said a lot of things are beautiful, but this takes the cake. So what is Euler's formula? Well, so if you have a polar form, I'm not necessarily going to explain this as much, but essentially this part over here, this sort of the unit circle part, is actually equal to something else. This is actually equal to e to the I times theta. This is very, very trippy to think about. Let's see, how do I explain this here? I can't necessarily prove this to you. But basically what I'm trying to say is e to the I theta is equal to cosine of theta plus I sine of theta. Again, I can't prove that to you. You can find proofs of it online, but this is what's called Euler's formula. And the most astounding result of this formula is what happens when you plug in pi. When you plug in pi for theta, you get e to the I pi is equal to cosine of pi plus I times sine of pi. And we can actually calculate what this is, right? What is cosine of pi? Cosine of pi is -1. What is sine of pi? It's 0. So this is saying that e to the I pi is equal to -1 plus 0I. Well, this is 0. So it's saying, let me write this down here. This formula is saying that e to the power of I pi is equal to -1. And that is the craziest result in all of mathematics. Your brain might be melting right now, but that's okay. Just know that this stuff right here, not on the quiz. But I did just want to show you just some really beautiful stuff that you can do with these complex numbers. It turns out that this result makes a lot of sense, though. It actually, the more you think about it, the more you look into it online, there's a lot of awesome videos out there. It actually makes more and more sense the more stuff you find out about it. But it's just so crazy. You have an imaginary number here, I, right? Most famous imaginary number. You have pi, which is, remember, that's a number that comes up that has to do with circles. You know, where's the circle here? Why is that showing up there? You have e, which, remember, where did e come up? Came up when we were talking about compound interest, right? E was this sort of like limit or this ceiling we could hit. If you compounded your interest infinitely many times, you couldn't get infinite money. You got E dollars, right? So that's there. And then you got -1. And -1 is just, it's like the first negative number you ever learn about. So we kind of have this one equation that ties together the most famous numbers in all of human history, all together, just in this neat, tiny little equation. It's just mind-blowing why that is even true. But anyway, I want to go ahead and end it there. Thank you guys for watching. Just know that really problems like these above are really kind of more or less what you'd expect to see on the quiz, as well as 6.4, which had to do with that dot product. So make sure you can do the dot product. I might do maybe a real quick example down here, right? 6.4 dot product. You know, if I gave you two random vectors, the dot product is essentially what happens if you multiply each component together, right? So this turns into 2 times 1, and then you add to it 3 times -6, right? So that turns into 2 minus 18. So in this case, the answer would be -16. When you do the dot product, right, you do it with two vectors, and you end up with a number at the end. That's kind of weird stuff. So anyway, also in addition, right, keep in mind that program I had that sort of simulates complex numbers raised to a power, like these problems in the middle here. All I want y'all to do for the homework is to go to that program when it's posted on my website. Let me go ahead and run it here. And I want y'all to take a screenshot of the craziest pattern you can come up with. So for the power, I might turn this into, let's raise it to the power 20. All right, let's get a lot of little complex numbers here. And just move that ball around and see, what kind of crazy patterns you can come up with, and just submit a screenshot of your favorite one. And you can raise it to as high of a power as you want. You could even do 100, and that will give you 100 little balls like this. Right? And remember, each ball is a complex number. So, I mean, complex numbers are some of the most beautiful stuff I think that exist in math. They're just, think about what this simulation is doing. It's multiplying complex numbers, but I mean, it's all got this like beautiful symmetry and geometry to it. So anyway, yeah, just submit a picture of sort of your favorite pattern there. That's a kind of cool one. And that will be that. Ooh, yeah, that's a nice one to end on. Yeah. So anyway, guys, take care. Have a good weekend. And make sure to study for that quiz. Right? It will be right after the weekend.